Hi, welcome to the Signal Pad. In this episode, we're going to take a close look and do some reverse engineering on this Anritsu MS46121A. This is a USB-based vector network analyzer. They're quite common. A lot of companies make them. And this one works from 150 kilohertz to 6 gigahertz. Now, this is actually part of the Shockline series, although this does not use the nonlinear transmission line technique to perform S parameters, which can be done all the way up to 110 gigahertz. Now, if I ever get my hand on one of those units, we will do a separate tutorial on exactly how nonlinear transmission lines are used to perform S parameters. But this is only 6 gigahertz, so it can be done using much more traditional ASICs that are widely available, and you can easily build a one-port network analyzer. Now, Anritsu is a fairly good company in terms of making network analyzers. We actually don't have a lot of equipment from that here in my lab. But this particular one is a broken one I bought from eBay. Unfortunately, I made a mistake, and I thought I bought the one that had a self-test error, but I accidentally bought the one that doesn't boot, meaning that it has a firmware fault. If you look at this data calibration on it, this data calibration actually goes up to essentially almost now. So basically means that this must have just recently died. Now with the bad firmware, I don't think I can fix it. But anyway, once we take a look inside, if you have an idea, you can let me know. But that doesn't stop us from reverse engineering it and completely understanding how it works. Now, a single port network analyzer is not as useful as a two-port one, but a portable unit like this one, which is USB powered, can be very handy in the field when you want to measure an antenna, for example, or a fault you might be detecting in the field. And because this is a network analyzer and can measure vectors, you can find distance to faults and things like that. It does have a Type N connector right there in the front, as you can see, and on the back we do have a reference, which is nice, so you can lock it into something which can be useful for calculating exactly a frequency that you're looking for. There's a USB micro deep in there somewhere, and there's a little light. That's really all there is to it. So the instrument is made of two halves, which is not that surprising. It's common to separate all the RF functionality from all the user interface and firmware and application side, and that's exactly what they've done here. There's a board-to-board interconnect from here to here, which what happens when you sandwich these together. There are a few other connectors which are probably for factory testing and programming and so on. We do have an Altero FPGA in here, which probably programs up when you power it on for the first time through an EEPROM that's sitting right next to it, and I fear that that's the corrupted part when of course we get no communication to the computer anymore. But I really want to take a close look at each of these boards and understand how they're made. Now, the casing of this instrument, no expense has been spared. This is machined from a single big chunk of metal, and it couldn't have been cheap, of course. Now this part is where the RF is housed. Now this piece over here is actually metal itself. This is a ruggedized way of connecting the USB into the instrument, and you can see that they have removed the paint over there so they can make connection with these copper pieces here, springy, so that when you close it all together you have a nice shield. And it's not surprising that you have to shield this very well, of course, because this is a network analyzer. Anything that gets in will show up directly in your measurements. Now it's a little bit surprising that there are absolutely no RF absorbers anywhere in this. I guess they must have taken all of that into account, and there are also no RF absorbers between the two boards when they are sandwiched together, because this is how they're essentially sitting together when they are closed, and all the RF side and the digital side are essentially on top of each other. But I'm guessing that they have done enough simulations and measurements to know that that is not a problem. So let's take a close look at all the boards that are inside of this instrument. I really want to dig into the components and also talk in details about the RF architecture and do some experiments which you may find interesting. Now, at the heart of the digital board is an Altero Cyclone FPGA, which controls essentially everything on this board, as well as communicates with the PC through an FDDI chip that's right over here. There's a serial memory EEPROM here, which downloads the content of the FPGA on power on. This is common, as a lot of these FPGAs are SRAM based. And this is, I believe, where things have gone wrong. I think the programming here is corrupted, and therefore the communication is either not good or something's wrong, and the program just simply hangs. There's a programming header over here, and if Anritsu had made any of this firmware actually accessible to the user, or just have a better way of programming it or reprogramming it through this USB port, this would be fixable. And of course, they don't share anything anyway, so it wouldn't help us. And then there's a couple of other components around that handle the power supplies and so on, which are not that interesting. You can see some power supply DC-DC converters over here, and all of that is passed through this connector to the other side, which programs the RF portion. Now we do have the external reference coming over here, and we have a PLL chip over here. This is a clock generator, programmable up to 200 megahertz or so. And you can clearly see there are some designated traces from this crystal and some designated traces that go over here, clearly generating the references of the RF part for the other side of the board. And we can see the part number of this. When we take a look at it, it's an analog devices IC with different references coming in. You can see the charge pump available all the way at the output right over here. You can control and tune something, and that's exactly what they're doing. That's where the closed loop over here is. There's a few other components here And here, this is for switching the external reference in and switching it in and out depending on whether it's present or not. And then there's detector circuitry that does that. So the digital portion is interesting. There's just not that many unusual things on it. It's just cool thing to see is that they are handling the RF reference generation on this side and passing it to the other side of the board, which is a little bit unusual, but I think it has to do with the lack of space on the other board. There's really not much room in there. Normally you want all of this to be handled on the same side. But anyway, that essentially covers this architecture. And here's the RF board, the photo from the top and the bottom, and I flipped the bottom one so they line up perfectly so we can analyze them more easily. Now, as with any network analyzer, especially a single port one, all you really have to do is generate an incident wave that you put into the device under test, look at the reflected wave coming back, digitize them at the same time, and the relative amplitude and phase gives you the vector information you need to calculate the impedance. And you do this after you've done a calibration. When you calibrate those two signals with an ideal open, short, 50 ohm, and so on, you can actually do that relative measurement. From that, you can compute the S parameters. That's essentially how all network analyzers operate. And this is no different, of course, which means that this is going to have two sources of signal. One signal to use as the incident wave, and another signal used to down convert the reflected wave. And those cannot be at the same frequency because you want to avoid the DC offset of all these mixers. You want to create an IF, and that's also essentially how most network analyzers are built. Which means we're looking for two identical synthesizers, RF generators. But there's one over here, and there's one over here, and they're indeed exactly the same. I'll show you the part number and what's inside in just a second. Which means that this guy is going to generate our incident wave. There's an amplifier over here to boost the signal out, and then that signal splits into two, but then it goes through this component. And this is a coupler, and we're going to do some experiment on this because there's some interesting things to consider. For now, just assume that this is a coupler. The signal going over here through the through path of the coupler goes over there and it hits the device under test. And that's our incident signal. And the reflected wave coming back over here also comes over here, comes through path over here, and then it goes out that way to this. This signal also couples this way, which becomes our transmit signal at the same time. Now you may say, well, these are not unilateral. There's going to be signals going in all directions, and that is true. And you can calibrate that, of course, out of it. That's one of the reasons why you have to perform the calibration. But essentially, the signal goes over here, hits the target, comes back over here, couples through, goes through this way, and then that means that we have two signals we need to down convert. One is over here, and one is over here, and from these two, we will have our incident and reflected wave that we need to down convert. So unsurprisingly, of course, they both go through a pair of identical mixers. This one going over here pops out of this side on the other side of the board. Similarly with this one, it pops out of this side, and then we have two identical mixers over here. And these mixers cover the entire frequency range of this S parameter measurement kit, which is up to 6 gigahertz, and their IF supports all the way down to DC. So they're using a very small IF. But these guys themselves need an LO signal, an offset LO signal, and that's exactly what this one is for. You can see it comes out over here, it pops into the board, pops out of the board over here, and it goes into an amplifier. This is a bias T for the amplifier to bias it, and that splits the signal identical into both sides. So you're hitting both of these mixers with this same LO at the same time with the same phase, which is exactly what you have to do because your reference and your reflected and your reference wave have to be digitized and down converted at the same time as well. Now this coupler is very interesting, so I want to talk about that a little bit separately at the end. But now you have generated an IF signal, and we have to see where that IF signal actually goes and how it gets digitized. That IF signal is just as important and just as sensitive as everything else on this board because it carries the S parameter information, and sometimes that signal can be extremely small, especially if you're measuring something that has a very good return loss. Imagine connecting almost an ideal resistor here. The reflected wave coming back is almost non-existent, which means that the signal coming back is tiny, and if you want to measure, say, a return loss of -40, you're going to have a rough time. And indeed, the accuracy of these instruments gets worse with the return loss getting better and better and better, which is not surprising. Again, this has to do with signal-to-noise ratio and signal integrity. So we can look at the X-ray of this board, and with the X-ray, we should be able to find out how those IF traces are treated. They should be treated just like the RF signals are. If you look at these mixers, these are the two mixers, right? That's these two. We're looking at them on this side of the board. And the RF side is right in the middle. That's where the LO was going this way and this way. We saw that. And if you look carefully, you can see that here's the IF. And look at that. They have stitched the IF exactly the same way as they would have stitched the RF. It's just buried in the interlayers of the board itself, and you can see the stitching right over here going through this area. That's exactly the same path you're looking at the very top. So they have really buried that and trying to protect it. There is this actually, in fact, you can see it right there. Okay, so then it goes into this component over here. Similarly, the IF on the other side sneaks in through here, also reaches this component. It's also hidden underneath the board. So we have to see what that is. So really the architecture of it is as simple as it possibly can be, given that it is a single port S parameter measurement. So here is what that synthesizer looks like. So I said that there are two synthesizers there, right? One of them over here, one of them over here. And that's what's inside of this. And you can clearly see that it does have a VCO that covers 3 to 6 gigahertz. And it has all kind of dividers. And by using these dividers and the VCOs, it actually has a bank of VCOs. You can close a loop around this, and it has a fractional N divider in there, and you can create essentially all kind of frequencies that you want and cover the entire range almost from DC all the way to 6 gigahertz using a combination of these two. So this chip that is sitting essentially twice can be programmed with a minor difference in delta F between them, and that would be the IF frequency of this down conversion, for example. Now here's a couple of information about these parts. So we have two op amps over here, and these two op amps are going to amplify and manage the IF signals before they're digitized. Not surprising, because you need to amplify these signals. And this is essentially a dual op amp inside. It's from Analog Devices. Now this component over here, where both IF signals first arrive at, is actually a potentiometer, a digital potentiometer. And I think they're just simply using that either to control the gain of these op amps, or just simply using it as a variable attenuator in order to adjust the value of the IF signal going into this op amp. And you need this because if the signal coming back is extremely strong, you don't need to apply a lot of gain. Versus if the signal is very small, you do need a lot of gain. So that's essentially what they're doing. It's a variable gain amplifier. And then you have an amplifier over here. This amplifier is going to generate the incident wave as I described. And that incident wave is going to be the maximum amount of power you can put into your device under test under S parameter measurement. And interestingly, it actually doesn't say what that is, but I think it's about 10 dBm. But there is a lot of loss in this path going forward. So the maximum signal the user can expect over here is actually less than 0 dBm up to 6 gigahertz, which is not very high. I would have liked to see a 10 dBm incident wave. For return loss, that's pretty important. So it's a little disappointing that it is so weak here, the output signal. And then continuing on to the other side, we have another amplifier over here. And this amplifier is used to boost the signal from the synthesizer, because now remember, you're hitting these mixers. These are double balanced passive mixers. You need a lot of LO power to hit these mixers. The loss here is not very high because it goes directly just split into two. And this thing has a power P1 dB of 15 dBm, which is a lot. So even after splitting it, you do meet the 10 dBm requirement of these mixers. And that's the double balanced mixer, as I mentioned. This is from Mini Circuits, of course. And then here is finally our digitizer. Now remember, the IF signal is very low in frequency, so you don't need a lot of high frequency sampling, or you don't need a very high bandwidth ADC to do this. In fact, this is only 3 megasamples per second. And then if you simultaneously sample both of the channels at the same time, which is one of the features of this chip, and it's very important that you do simultaneous sampling, because the phase difference between these signals is the incident and the reflected wave. You need that information. So at 1.5 megasymbols per second per channel, you can imagine that the IF signal has to be in the hundreds of kilohertz, which also quite makes sense. Now let's talk about this component, because I think this is interesting for us to take a look at and also to build a little experiment out of. So let's see how this works. So this is a coax. Okay, this is a coax line inside, sitting in the middle of this PCB. Notice how the body of that coax does not touch the ground plane at all, only does at one side. So what you're doing is that this is the center of the coax. You're injecting a signal into the center of the coax while grounding one side of the coaxial body right at the point you inject it. So this is basically your RF ground over here. And on this side, instead of shorting this to the chassis again, you tap it off as another signal. So here's the outer shell of the coax, and here's the inner shell of the coax. But what is this? Well, this is basically a balanced to unbalanced conversion. It's a balun. It allows you a single-ended input to be converted to a differential output. And then it splits the signal into two. You have a phase reference of 0 degrees on this side and a phase reference of 180 degrees on this side. So it's a coupled line. Nothing unusual. Coupled lines are used all the time to create this kind of signal splitting. This is very useful in a network analyzer because essentially your incident wave can be tapped off on one side, and that can be your reference signal. And the signal, when it's reflected back, goes right through on this side and then is split on the other side. So that all makes sense, and I think is used quite common. But then what's the deal with this ferrite core over here? Well, it turns out that because this is such a short length of cable, as the frequency gets lower and lower and lower, the magnetic coupling between the inner and outer shield of this coax is not very strong anymore when you're close to DC. And you end up having almost no coupling at very low frequencies. You need to somehow confine the magnetic field and push it and maintain it on the inside so that you can get strong coupling even at lower frequencies. Well, if you add something with a high permeability constant, like a ferrite core around it, it does exactly that. So by doing that, you extend the frequency of this coupler down to very, very low frequencies and close to DC. It does that at the cost of some high frequency loss, but essentially, instead of having something that couples really weak and then gets stronger, you get something that's a little bit like this. So you sacrifice some high frequency coupling, but then you get a much more flat response. Well, this is a really simple structure. We should be able to just build something like this in a very crude way and try it and wrap a core around it and see, does it really extend a low frequency coupling or not? That would be an interesting experiment. Let's try it out. And behold, this masterpiece coupler I just put together. So it's basically exactly the same structure. You have a coax coming in over here. The coax then on the other side splits, and the inner and the outer core are connected to two different center taps of these particular SMA connectors, and there's two resistors hanging on the side just to balance things a little bit. Again, this is of course not optimized in any way, just something I quickly put together, but it does allow us to investigate the exact coupling behavior. We can see how the signal couples from here to one side, couples from this way to the other side, and of course the coupling from here to here, which means that this should have some directivity hopefully, which is the whole point of using it in the network analyzer, which I think I may have forgotten to mention earlier. And I'm going to wrap this ferrite core right around the outer edge of this live during measurement and see if it extends the coupling to lower frequencies during S-parameter measurement. Let's try it. Okay, so here's our measurement setup. We're going to use the Siglent SNA 5000 series, which I've done an extensive review and teardown of. Part 1, Part 2 is going to be also coming up soon, hopefully. And we have a 3-port S-parameter measurement. We're basically connecting port 1 to the input, and then port 2 and port 3 to the through and coupled path of this coupler that I made. I'm also making the appropriate measurements over here, and we have our ferrite core, which I'm going to wrap around this at the appropriate time. So I think it makes sense to focus on the screen so we can describe what it is that we're measuring. Okay, so here are all the relevant measurements at the same time. Now, S21 is what happens in the through path. S31 is the coupled path. So essentially you want these two to be identical in magnitude. That's a perfect coupler, for example. Here we have S32, which is the coupling between the coupled to the through path. You ideally would want this to not exist at all if you had infinite directivity. But you do, at least in this case, you want it to be a little bit weaker than the other two, showing that there is some directivity. And then we have the phase of the through and the coupled path. Let's start with that one. We said we expect about 180 degrees out of phase. And if you look at that, it's, you know, it's close, it's reasonably close. And again, this is not optimized at all, but we do indeed have almost a 180 degree splitter, which is what we expected to find. Now keep in mind that this is completely non-optimized, and all those resistors and capacitors that you saw in the PCB is all the art of tuning this to getting the perfect response. Now if you also look at some of the higher frequencies, just remember this goes to a gigahertz in this case, around here you can see that the insertion loss of this coupler is about 2 to 2.5 dB, which is not great. But again, this is not a very good coupler. But indeed, the magnitude of the coupling around 1 gigahertz is roughly the same, which is good. That's also what we would expect. You also see that at lower frequencies, we do indeed turn off very, very quickly. So for example, at 30 megahertz over here, we only have minus 15.6 dB of coupling in the coupled path, whereas the through path gets stronger. Why? Because the energy is not getting to the coupled path, so you see more of it on the through path. And we want to essentially transfer some of this to that side to get a more flat response. And you also see that the coupling between the coupled to through path is weaker, then this thing indeed does have some directivity, which is also great. So now I'm going to take this, I'm going to wrap it around the coax. That's all I'm going to do, and keep an eye on this live measurement and see what happens to the slope of these two. Here we go. I'm going to first just place it on the line like that. Okay, and I'm going to slowly close it, and you can see, look at that. Isn't that amazing? As I close it up, we get better response at lower frequencies. I'm going to go completely clip it in now. And here it is. Look at that. Isn't that just magic? It went from -15 to -8. Now it can still obviously be optimized further, but this clearly demonstrates that that effect that I was talking about confining the magnetic field, allowing more of the coupling to happen at lower frequencies, is 100% a real phenomenon. You can also see that the phase improved a little bit at lower frequencies, and this guy also improved as well. But you still have some room to go, and you can play with the different ferrites and their distances and even the gaps in between them to perfectly tune this. It really is an art, but this phenomenon indeed works. There we go. Look at the bottom. Look at that. That's all I did. Just wrapped it around and clipped it. And this is actually 2 pieces of a ferrite because I can only wrap it around like that. In those situations, they slide it in before they do all the soldering. So it's even a better ferrite connection. Now, if I had done that, then I wouldn't be able to take it off for me to show you. But this indeed absolutely demonstrates this phenomenon. And there you have it. I hope you enjoyed this video. As I always want to thank the Patreon supporters who make this possible, allow me to buy these things broken with no chance of repairing them. But it opens up these kind of conversations where we can dig into some subtle design and really take it to the final measurement stage and hopefully create an intuition for all of you who are interested in this field. As always, I'll see you in the comment section.